Today we're going to look at my Commodore PET replica that I started in 1989 and have been working on ever since. Today I'm going to present you the current version of the machine in all its glory. So stay tuned and let's have some 8-bit time. In 1989, when I started studying, I was working on my own Commodore PET replica when I found that there was a game that I played on my school's PET 3032 that I wasn't able to actually port to the Commodore 64. So I decided to build the machine based on such Eurocard boards with a DIN connector plugged into a passive backplane, perf board. Typically all of my first boards were perf boards and were soldered like this, not even like every single wire was soldered separately. In the meantime, things have become much better, and I have been producing boards and so on. So let's have a look how that machine looks today. I have also put it into a case that I built myself, and so let's have a closer look. The case is basically plug and play. You can just remove the stuff like that, and you can see here we have PC disk drives, which are not the typical Commodore disk drives. We have a CD-ROM, and you can actually see a hard disk. And to have a better look into the machine, you can actually take out all the parts. Like here we have, can take away the keyboard, put that away. And here you can see there is the, I should have probably cleaned it up a little bit. It has been lying around for quite a while. So here is the CD-ROM board. Here is my very first hard drive that I initially had connected to my Atari ST, which I used as a hard disk for my Commodore 64 and the PET replica, which is now part of my PET replica. It's a Seagate ST1096N, which is a SCSI board, SCSI drive. And here we have a IBM branded Seagate Cheetah 18 gigabyte wide SCSI-II disk drive, and that's also connected to the SCSI bus using a wide to narrow SCSI adapter. So if you look at here in the top, we have here a PET SD board, which enables me to connect to the PC as a disk drive for this machine. Here is a composite video generation board, which we can see the output on when we look at the back side. And here we have the board with the disk drives. And we can move that up a little bit. And here we see the whole machine with all the boards in here. This is the passive backplane. I've added some more connections for power supply, and then we can have a look at the boards when you look at the back of the machine. So let's have a look at the back side of the machine. So we have the power supply here. We have all the boards here. We have some controls over here. So let's start with the controls. There's the reset switch. Here is a switch for the CPU frequency to go from select between 1 or 2 megahertz. The power supply switch, composite output. This is unused, and here is a PET SD, which I got from the creator of the PET SD. Thanks for that. That I have mounted in here. which is connected to the board here. Looking at the boards, I have a SCSI board here with a 50-pin cable to the hard disk and CD-ROM drive. I have a board for Ethernet and USB. Then there's the CPU board with the cable to the frequency switch. Then there is the video output, which goes here to the composite generation board, which is mounted on top here. And this cable connects to the PETIO board because the PETIO board requires the vertical blank signal to generate the interrupt and also controls the character ROM. So those two signals are not on the bus, so I have to have that separate cable. So this is the PETIO board. It has a cable for the keyboard. This goes to the IEEE 488 to the PET SD, and I can also connect some more devices on this connector here. Then there is the RAM and ROM board with a serial interface, RS-232, and there are some open slots left, and this one is the floppy controller. So here this cable goes to the floppy disk drives, 34-pin sugar bus, and then here is the serial IEC bus for serial Commodore devices. So what's so special about that machine? What I wanted to achieve was to really expand the Commodore PET and be able to use much more memory and be much more flexible and really use the way use the bus to provide a much larger address space. So what you see here is the CPU has an address space of 64K, which is divided into 16 pages with 4K each. The bus has an address space of 1 megabyte. So it's not got 16 address line but 20 address lines. So we have 1 megabyte of physical memory. In that physical memory, for example, the RAM and ROM board, BIOS board as I call it, has a 512 kilobyte RAM chip on it, and it also has a 32 kilobyte or 64 kilobyte of a ROM chip on it. And this RAM is mapped into the upper 512K of the 1 meg, but it also has the boot configuration where the lowest 32K are of physical address space are RAM, and the next 32K are mapped to the ROM. Then I also have the video card. The video card has 64K of DRAM, which is used to create the video output, and so we have in total 500K plus 64K of RAM available in this particular machine. There are other boards that have some more memory that I could put in there as well. So how does it work? I used an MMU chip, MMU, Memory Management Unit, 74610, which provides a mapping from 4 bits to 12 bits. In the beginning I used 8 bits of those just for address lines. So I have the mapping from the uppermost 4 address bits of the CPU go to the uppermost 8 address bits on a memory bus. I have 16 registers that I can set to the different values, so I can map each of the 16 4K pages anywhere in that 1 megabyte of memory. And that's what is the default setting that is used when I run it as an emulated PET. So I have the lowest 64K basically from the BIOS board, which is the boot configuration, except for the address at 8000 hex, the 4K block, which is from the video RAM. So the video chip is configured to create and take the video output data from there, and at the I/O area at E800 to EFFF, which is handled separately. So on the bus you have two types of cards. You have the memory cards and you have the I/O cards. And the memory cards, they have to look at the whole 20 address lines for the physical memory. The I/O cards only have to look at 2K address space. So they usually have an 8-bit compare chip, or the 74688, and that maps out 16 bytes of address space inside this I/O space. So that's a very simple way of selecting a small and usable range in the I/O space. This is the setup that I originally used in my GeckOS operating system. This operating system is a multitasking operating system, and because I had the MMU, the original version 1 of GeckOS operating system didn't have relocatable files, but just every task had its own memory from the physical memory mapped to basically page 0 and as much as it needed into its own memory space. So there was no need for relocating memory programs into different memory areas, because every program had its own memory. Of course that has changed, but this is the original machine GeckOS has been written for, and that's where GeckOS comes from. Let's look at the SCSI functionality. So let's load a small test program and let it run. This is resetting the SCSI bus, then looking at the devices. So it's detected the 80 megabyte drive, then it's detecting on ID 2, it's detecting a device on ID 3, which is starting right now. That's the 18 gigabyte wide SCSI-II drive, which once started will show its size and so on. And then there is the CD-ROM drive as well. And then it tries to scan the PC partition tables, and only the 80 megabyte drive has some partitions in there. The 18 gigabyte drive has no partitions right now. So let's talk about GeckOS. GeckOS actually only works on this machine right now, still in version 1. There is a version 2 of GeckOS which is running on the Commodore 64 and the PET and so on, but this one I haven't been able to port it yet in time. So let's load the operating system and start it up. Press the keys to start. Takes a moment until the video grabber syncs, and then there we are at the shell. And if we press the add sign here, we switch between two different consoles that you actually have, and then we can have we have the directory command that shows us here on drive C is drive 8 on the IEEE 488 bus, which is going to the PET SD and then to the PC where I actually loaded the operating system. And then we can also have drive E, which is the 3.5-inch floppy disk drive. And this hasn't been ported to version 2 of GeckOS as well, so that's still to do. And drive F would be the 5¼ inch disk drive. So as you can see, there are some disks. If you look at the tasks that are currently running, you can see there is the device tasks, which is actually providing the devices as files. So you can actually open a video device or a serial device as a file, similar to the Unix mantra that everything is a file. Then there is the FSIEC for the IEEE 488 bus, FSIBM for the floppy disk drives, the shell which I'm running here, and then the monitor which is running on this side. Now here's a feature that I'm kind of particularly proud of. What I've done is I have added a micro PET, which is my new modern PET replica, on top of the old one, and I have connected the micro PET using the IEEE 488 cable with the PET SD here on the back of the old machine. So, and the idea is to actually use the old machine with the GeckOS operating system as a disk drive for the micro PET. So as you can see, we still have GeckOS running here. Then we also have the micro PET running, going into the boot menu, and then we can try to load a directory on the micro PET, and this one is coming from the PET SD, which it takes it from my PC, but we can also have it from unit number 10, which is actually the GeckOS. So what you have here is you have the same directories that we have on the GeckOS with drive A, which is actually drive 0 on unit 10 on the IEEE 488 bus. And just as well, we can try to load drive 4, and maybe you've seen it here, the flashing on the sorry, the wrong one, flashing on the 3.5-inch floppy drive, and this is the one that we've seen previously as content of this disk drive. Or we can also say we take drive 5 on unit 10, and you can see the flashing on the disk drive here, and there we have it. So the GeckOS can run as a file server for IEEE computers on the IEEE 488 bus, which is cool, I think. So there are 3 reasons why it took so long for me to record this video. First of all, I had to fix a bug on the RAM-ROM card, because I was using the ROM chip. I wired it according to the specs, but because I switched it basically off and on every time, every clock cycle with the clock, it was really producing too much noise on the data bus, and that caused the machine to become unstable. I had to find that one. That was really hard because I've been looking for that for quite a number of years. The second one was I wanted to show the floppy disk drives, and I knew the floppy disk board was working because I had been using it as a 1581 emulator, but those were only 2 cards on the whole bus. Now we have about 10 cards on the bus, and so I had to find that I had to not use the 16 megahertz clock from the bus, but had to have an own 16 megahertz clock oscillator on the floppy disk drive. And the third one is I also wanted to show some of the SCSI functionality, and obviously I had never even tested accessing the 18 gigabyte hard disk, and just assuming that it would work, but now I had to find out how to handle this one, because that was something that had to be handled much more carefully, much more so somewhat different than the older 80 megabyte drive, which is just switch on and then wait for it to spin up, and then it's there. For the 18 gigabyte drive, you have to give it a start unit command, etc., etc., looking at error codes and stuff and handling them and so on. So that also took a while. So what's next for that machine is this will be now, as it is, a standard supported operating system on GeckOS. So I will have to port GeckOS 2.0 onto that machine still. It will also have the feature to run as a bus, as a disk drive for other computers on the IEEE 488 bus. There will be support for PC partitions on the hard disks with a FAT16 file system, or maybe even larger. We'll have to see how I'm going to implement that one. So yeah, there is still some things coming, but on the other hand, it'll be slow because too many side projects, I have to admit. So after that part of the video, I will be showing of some number of boards that I have been producing over the about 30 years that I have been working on that machine, which are some very nice things like a block transfer engine, like a coprocessor and stuff like that. So if you're interested, you can watch it after that, but if not, that's totally okay because it's lengthy. So I just want to say thanks for watching, and see you next time. Recently I had to look through my kind of archives to find an older board that I had. So I'm using this opportunity to show off some of the work that I have done in the last basically 30 years with my self-built computer based on that passive backplane. So what I started with is this backplane here, with a single self-built power supply. Actually still exists with a single poor 5-volt regulator in here, which got pretty hot. Therefore it got this huge heatsink, and there's actually some battery buffered power supply here. I should probably remove those batteries now. Yeah, and those are standard DIN connectors that you still get today, and all of the boards have those connectors. So let's get through the boards. So first of all, the CPU board, and here I want to show off. This is the very first one I built, and as you can see here, it's got a lot of extensions that I added later on. Even here some flying stuff. It's all built on perf boards with every single connection soldered separately. Yeah, quite some work, quite some experience. Really nice time that I had, and somewhere else I have from all the other boards. I have those perf boards as well, but nowadays I'm really using really produced PCBs. So what did how did the CPU board look like? So there is the CPU here, or maybe here. I think this was the CPU, and that was the MMU. And this was the thing that made the system special, because the MMU mapped the upper 4 address bits into 8 new address bits. So the whole bus has a address space of 1 megabyte and not of the 64 kilobytes that the 6502 has natively. So that was really great. And it also had a separate select line for a 2 kilobytes of I/O window. So it was much easier to select I/O space in that 2 kilobyte, with just using an 8-bit compare chip, which is basically on all of those I/O boards that I'm going to show. So yeah, that's how it started, and you can see it's getting better. Then I have them produced. I do have some older ones somewhere where I did try some self-etched boards, which didn't really work. This is produced already. All the boards have their and don't think you can see it on the camera. Have their name and version number on put on this copper layer, and this is basically the latest version of that. And here you can there's still no printing on it, but at least solder mask is applied to the board. And it's still the same. There's the CPU, there's the MMU, which is 74LS610. So it's still basically the same thing. What's completely different here is this one. This one is 65816 CPU board, and it actually runs at 8 megahertz. Those run with 1 and 2 megahertz. This one runs with 8 megahertz. Got its own ROM and RAM. Got the logic in the CPLD, and still runs the bus in 1 megahertz. So you get more speed from that. If you look up, the 74LS610 was used in the early PCs in a variant. I think there was the 611 in there, which could be somewhat converted, but I made because you basically can't get them anymore. So I actually made a small replacement board that you can put into the socket of the MMU using fast cache RAM chips. So that's just the CPU. So what is the CPU going to execute? So this is the RAM-ROM board. I called it BIOS board, basic input output, more or less, because well, it's got the ROM, it's got some RAM, it's got a serial interface, it's got a UART here. The original board, perf board version, had an Akia 6551, but I found it too not powerful enough, so I switched over all the boards to a UART, the 16-byte FIFO buffer. You can have up to 512K RAM and 512K ROM. Then there's a lot of jumpers that you can use to configure them. But basically, what it does in the lowest 32K, it maps RAM, and then it maps ROM in the second half of the bank zero, and you can map the other stuff elsewhere in the 1 megabyte address space. So that's that. Then there is the video board. So this is based on the 6845 or 6545 board. Got 2 DRAM chips for video memory. This is the character ROM. Yeah, this is output with separate sync and video signals. So somewhere I have these adapters to create composite out of this, and it's also got, you have 64K of RAM here. An interesting thing is using the MMU, you can map any of those memory spaces anywhere in the CPU address space in blocks of 4K. So that's very nice. So the original purpose of that machine was to create a PET replica. So, well, this is CPU, this is memory and a video output. So basically this is the board that combines all the Commodore PET I/O. So you got the VIA, you got the two PIA chips, you got the keyboard interface, IEEE 488. You even have the beeper, user port, and so on. So in the original perf board version, those were two boards because I wasn't able to did that type of integration back then on perf boards. So, but this, but in the meantime I have integrated all that on the single board. So those four boards here, maybe not this one, they make up a Commodore PET 4032. In an extended version, you have the MMU and so on. So that's pretty nice. However, it gets even better because I also at the same time developed some single PCB computers. So this was called the GeckOS machine, which is a single processor, 6502 RAM, ROM, or the other way around, I don't remember. This is a VR, this is a UART, and then you had a serial Commodore serial bus interface here, so you could use that to communicate with the Commodore devices, and and this is serial interface. So this was also able, you could plug that into the backplane and use all the I/O cards. So there was a memory mapping, not the memory cards, but the I/O cards at least. And then I changed this one and removed the VIA and the serial bus. So, and this is what I call now the PET CPU, which is basically CPU, UART, RAM, ROM, and that's it. Also a lot of options to configure it, and then basically these three cards, the PET CPU card, the PET I/O card, and the video card, they make up a PET 4032 as well. So, and as you can see, I'm a big fan of the Commodore PET. So I have also created an adapter to use those I/O cards on the PET. So you can put that under the CPU on the Commodore PET, and you can plug in one of those I/O cards here. And this is an add-on, a later add-on for 3.3 volts generation when I extended the bus interface to include a 3.3 volt supply as well. So this is actually a newer version where you can actually put in two I/O cards. Well, it depends on the space you have. And this here, those here, this is the perf board version. This is for the Commodore 64. So you could use the I/O cards and or even the memory cards, because this VIA here does an address extension on the Commodore 64. And this is the newer one. And here I made a mistake because actually when you plug it in and put the I/O card on the side, you basically have a problem with the cables. But anyway, it's a first design. Sorry, this doesn't belong here. It's actually my 65816 accelerator board for PET. So let's have a look at some of the older cards and some of the special cards that I've built over the years. This one here is PC floppy drive interface card. So you have the WD 1772 here, and there is a VR to control the other control signals for the sugar bus. You can use standard PC floppy drives on that one. This one is a newer version, and it also introduces again the Commodore serial bus, and it's also using the CIA variant 8520. So basically, if you use a PET CPU board, the one that I showed before, and this one, you can actually have and build your own Commodore 1581 disk drive. This was the 3.5 inch floppy disk drive for the Commodore C64 computers and so on. This is the original SCSI board. Also, you can see it's only just a couple of integrated circuits here, chips. It's only doing the async version of the SCSI interface, but that's what SCSI-I does. You can use it. You don't need to use it in a synchronous mode, but you can use it in asynchronous mode, and it's perfectly valid to run it from a 6502. And you can see this is the newer one, which is produced already. This has also got I think an I2C interface here as well, or something like that. Yeah. Anyway, at some time, I had to combine other stuff to fill in the space for the boards and stuff like that. So, what's this? As I mentioned, the address space on the bus is 1 megabyte. You can use this board to actually replace a 6502 CPU on a different computer, and map the address space of that machine that you connect this cable to here into my CSA computer. This is actually what I did to develop updated ROMs for the 1541 Commodore disk drive. I put in this cable here, and because all the memory, all the system is run from the PHY-2 or from the clock here via that cable on the floppy disk drive, I was able to map in the 64K address space of the floppy disk drive. Of course, not all of them is used, but anyway, here into my machine, and I was able to replace map with the MMU, the I/O space and RAM, but not the ROM. And I'm using RAM instead of ROM, and so I was able to run a modified ROM and test modified ROMs before I had to burn it into EPROMs. This is basically a dual ported RAM. It's actually 2K, 2 times 2K static RAM chips, and they are clocked in from the bus, and then and half the clock here from the bus, and the other half of the clock is from those I/O ports, and you can connect this actually to a keyboard connector on the Commodore 64, because all that what the C64 does is when it scans the keyboard, it puts out a row, and then it reads in the column value, and that's basically using kind of RAM, and that's what this board does. This is one of the more complicated boards, and I called it Blitter, but it's actually some kind of DRAM engine. So basically what it does is it allows you to transfer blocks of memory from one location on the bus to another location. It's all SMD, it's very light, still very much packed. Yeah, quite some interesting experience to build that thing. So here I wanted to reuse the SIM modules that I had laying around from older PCs. I wanted to reuse them here in my self-built computer, and I found out that the SIM socket just perfectly fits into like this on the Eurocard, and I tried it and it didn't work. And I got into discussion with Bill Hurd, the designer of the Commodore 128, and then I learned a lot about well, the power hunger of those chips and what you need to do. And so the result is actually this board. This then actually works. Puts a lot of logic, the whole glue, refresh logic and so on into the CPLD. But the main thing here really is it's got this separate power connector, it's got terminator resistors for the data and then address signals, it's got in series resistors for those, just to make sure to have that properly decoupled from the actual main logic, so there is not too much interference, and then it really works. This one here is a coprocessor. What you can see here, it has two connectors for the bus. One you can plug into the bus itself, and the other one you can actually plug in a second I/O card. And here is a 6502 coprocessor. It's got 64K shared memory with the on the 1 megabyte address space on the main bus. And you can either use you probably see it here. Those are RAM and ROM underneath the space, so you can use it with RAM, or RAM and ROM as you need to. And you can have an I/O card here, so basically you can use that as a SCSI coprocessor or as an Ethernet coprocessor, whatever. And this one is also a very interesting one, because the MMU actually has 12 bits. It maps those uppermost 4 address bits into 12 bits. I use 8 on the address bus only, but the other 4s, I think 3 of the 4 are used for write protection if the mapping is actually valid, or if execution is allowed. So it's actually got a no execute bit, but it doesn't help if the CPU doesn't react on it. So if the main CPU board detects that the main CPU wants to access a page that is not mapped on the MMU, or it wants to write to a write protected page, or it wants to execute on a protected page, some error lines on the signals on the main bus are set active, and then this CPU can then stop the main CPU using the ready signal, take over the bus, and take over the bus, and then do what it's needed to resolve the situation. You can actually also use it to single step a program. Yeah, you can run that and have it react on the sync signal of the CPU, and use that one to actually read out the address that the main CPU is doing. And you also have the capability to attach another I/O chip here, so for example to swap some memory in and out. So how has the machine aged, and what have I learned? First of all, over the years the electronics have gotten faster, and you have faster switching times, and so I started to get into problems with the reliability. It was rock stable when I ran it back in the days, with 1 or 2 megahertz even, all LS, TTL, LS logic, stuff like that. But it seems it's gotten more difficult with the ringing on the lines because of the fast transition times of the signals. So I started working on terminator boards that you have to put into the first and the last slot of the bus to do some termination on the data and address lines. Yeah, I worked on this is first power supply board. It included the battery buffer from the original backplane here on the board, and yeah, but in the end I found out I really didn't need that, and I don't especially I didn't need it in that size. All the you could battery buffer the SRAM on the BIOS board, but basically never actually used it in that way. So I made it smaller, like this, and there's actually a newer version which I have somewhere in my machine that has the terminator resistor networks included as well. So looking at some more advanced interfaces, this is a board where I started working on Ethernet and USB, as you can see here, and this is the CS Crystal 8900A chip, which I actually soldered myself onto this adapter board just to make sure if I break it I can I can do it again without having to reproduce the whole board, stuff like that, because this is one of the first and more difficult, most difficult SMD chips I had to solder at that time. There is a small USB chip here and another one here, because actually that was running out of production, so I had to switch from PLCC to SMD version, and that's the Cypress SL811. So this is one for, as you can see here, one is for device and one is for host USB. So both of them work. So you can actually use my machine as a keyboard for a PC, or the other way around, you can use a USB keyboard on that machine, on my machine. And this is an Ethernet card that also works. This is a whole Euro PCB. And then when you think, how you can shrink that a little bit with this board, and it could have been even smaller. There are two variants, because this is a 3.3 volt version here, so I had to do some signal level translation, and I built in two options onto that board to test it. So it worked out both ways. I was lucky. And this one is actually the highest density I got. So this is the actual, the upper part here is the actual I/O stuff. So you have a USB host, you have a USB device, or vice versa, I don't remember. There's an Ethernet chip here, and there's the SD card, and they are this is a 3.3 volt section, and it's using SPI interface to communicate. And all the lower part here, this is actually the bus interface. This is the level translation, this is the SPI interface, and this is to select the I/O space and so on. So this really gave me the motivation to look at how can I actually integrate more on a single PCB board, if this already this is just this small part of the PCB that actually is required for all those USB and Ethernet goodness. And that's one part that led to the MicroPET, where you can see in my previous videos.